All right, welcome everybody to today's HIT seminar. We have Spencer, our own Spencer Klein, which needs absolutely no introduction, except he's the state-of-the-art scientist in ultra-peripheral collisions, everything you need to know about photon-induced interactions, and he will speak today about quantum mechanical phenomena in UPCs in relativistic heavy ion collisions. Spencer, thank you very much for being here.
Sure.
And the floor is yours.
Yeah, so this is small group, so I can be pretty informal, which means if you have questions, please speak up. There are certainly things in this talk that could inspire vigorous discussion. Talking about quantum mechanics, basically two main topics. One, which some of you may have heard before, it's about the good Walker paradigm, and I'll talk about where it fails and why this is important. And then we'll segue to a bit of an aside about going beyond the Pomeron, looking at coherence with region exchange. And then I'll be talking about multiple vector meson production, which is some new stuff, which I think you'll find very intriguing, and gets a lot into things like wave function collapse, things you don't normally talk about, but I will show has some observable consequences. So most of what I'm talking about involves exclusive production, and this is very important. It's a cornerstone of all ultra-peripheral collision studies and of the planned EIC program. It's the primary method. It's our primary method for probing the low X gluon content of protons and nuclei. And this occurs via reactions like I've shown here. We have a photon interacts with the Pomeron to produce a vector meson. The Pomeron is mostly gluons, so it probes the gluon density of the nucleus. But important is we can go well beyond just the gluon density. We measure the transverse momentum that gives us information on the transverse distribution of gluons in these targets. So it can not only tell us how many gluons there are, it tells us where they are. And then incoherent production, where the ion breaks up, is said to be sensitive to event-by-event fluctuations. These are things like gluonic hotspots. So the formalism for this is something called the Good-Walker formalism, developed by Good and Walker in 1960, and if you want sort of the definitive paper that fully developed it, it's Meitner and Pumplin in 1978. Anyway, it links coherent and incoherent production to the average nuclear configuration and event-by-event fluctuations. By configuration, we're talking about the positions of the nucleons, positions of the quarks and gluons, the number of gluons, the presence of gluonic hotspots. And it defines explicitly coherent means the nucleus remains in the ground state. Therefore, you sum the amplitudes and then square. So you're essentially averaging over the different configurations. The incoherent cross-section is just the total cross-section, and then you subtract off the coherent. To get the total, you square the amplitudes and then sum. So you're talking about sum of squares minus square of sums, and that you immediately recognize as a variance, and you get this. So see how it is sensitive to fluctuations. You can go beyond that. I mean, there's this formula here, which is basically relating coherent d sigma dt, this amplitude. Now, t is pt squared plus pc squared, and for the purposes of this talk, it's just pt squared. The interesting thing, of course, is that pt and impact parameter are conjugate, so d sigma dpt encodes information about the transverse locations of the interactions. We can get that out with this two-dimensional Fourier transform shown here, and that gives us f of b, which is the transverse distribution of the targets. Here by targets are quarks, either nucleons or quarks or gluons. Do it either way. There are many caveats in this transformation. I'm not going to go into all of them here, But there's this issue of the range of integration. Of course, Fourier transform goes to from zero to infinity. The data is cut off at some maximum PT. Imposing a maximum PT, essentially you're convoluting the actual nuclear density with a square function. There's issues, something called windowing. There's an issue that the sigma dt, it's you're taking the square root. There's two solutions to a square root, positive and negative, and you should be flipping the sign of the square root of the sigma dt after each diffractive minima. There's issues with photon PT. There's issues in finding the diffractive minima, etc. So this is actually a rather difficult technique, but when you get it working, it's very promising. Get good stuff out. So as I said, the incoherent cross-section accesses event-by-event fluctuations in the nuclear configuration and deviations from the mean. And here, though it's still put in this form, d sigma incoherent dt, the connection between T and impact parameter is weaker than in coherent production. You can't actually turn a crank and get out a specific distribution, but you can use it to test models. There is some T sensitivity here. The problem is shown nicely on this plot here. You'll remember with Goodwalker, I said that coherent is defined as the nucleus remaining in the ground state, but the problem is we also see coherent production even when the nucleus is excited. And this has been seen in most star UPC analyses where you're actually looking at a diagram like this shown here in the lower right, in that the trigger requires that the two gold nuclei be excited. So that, this trigger requires that you not have the reaction not be coherent, a la Goodwalker. And this plot on the upper right shows some data from STAR. This is an older analysis, but I think it illustrates the situation nicely. You can see that the sigma dt can be described as the sum of two exponentials, one corresponding to the slope corresponding to the size of a proton in red, and the other showing the contribution or component consistent with the size of a gold nucleus. So, in other words, even when the nuclei break up, we also see this coherent enhancement. We're here defining coherent as a peak with PT. Yes?
No, sir, finish your sentence.
PT less than H bar over RA. Essentially, you're adding, it's like you're adding the amplitudes here for P, where the phase doesn't matter much. I'll say more about that later. Go ahead.
Maybe something stupid, but an occurrence where you have a coherent and incoherent interaction in the same event, and your trigger triggers on the excited nuclei, but there was something else happening in that event that would give you coherent interaction. Is that excluded? Or?
Well, I mean, normally would say you have coherent or incoherent. You wouldn't have them both.
Mm-hmm.
And here the signature generally for the nuclear breakup is the fact you see neutrons in 0-degree calorimeters.
Yeah, I understand.
You could also have a photon exchange that's more energetic and produce a delta, for example, in addition to the vector meson.
Yeah, but not all of the nucleons, if I may, not all the nucleons participate when you have an inelastic process. So do you have the same A dependence as in the coherent?
As far as we can say, yes. You can ask that question again after my next slide.
Okay.
Which is directly. So anyway, this is not unique to STAR. Alice did produced a very nice paper that, also measuring coherent photoproduction. They had a trigger where they did not require nuclear breakup, but they were able to see neutrons, and they see the same coherent peak in events with no neutrons, with neutrons on one side or neutrons on both sides. And you can explain this quite nicely with these diagrams where you have independent photon emission. Each photon does one thing, called this factorization. Although if you go to a higher PT, you can have a single photon which could produce a vector meson and excite a nucleus. But that's kind of all moot if you're talking about good Walker. It does not have an exception for mostly separable reactions.
Sorry, so they're not really the experts. So could you again explain the figure on the right hand side? It's blue is the cross section from
That is, has a slope that's consistent with h bar over the nuclear radius. I will have more on this later. I talk about an alternative approach. So now getting to Jerry's point, that we don't just see photoproduction in these ultra-peripheral collisions. We have now observed them in peripheral collisions going down to relatively moderate centralities. And this has also been seen by both Starr and Alice. The upper right-hand plot is from Alice at 70 to 90% centrality. And you again see this peak for PT less than h bar over RA. And then here on the lower plot, we have Starr data where this is centrality 40 to 80%. So these are not even particularly peripheral collisions. And they've plotted the sigma dt, and what they see is a slope that is consistent with what is seen in UPCs. In other words, there is no clear data that some of the nucleons do not participate. There's also 40, 80, you might expect to see a change. There are a bunch of questions here. How large is the target region? As Jerry was saying, is it all the nucleons or just the spectators? Star data is consistent with them being all. It's a little bit trickier because there's an interference I'll talk about later, which is more prominent in peripheral collisions with smaller b. The other thing that is relevant and we don't yet have good data is what is the cross section, because photoproduction and these hadronic interactions have similar time scales. So even if you assume that the hadronic interactions don't affect the coherence, you still have a question of which came first, the J psi or the hadronic interaction. Because if the hadronic interaction comes first, then the nucleons will have lower energies, and so the photoproduction cross sections will be lower. And clearly, if you're going to do a proper calculation, you need to consider both cases. But there's a lot to think about here. You also, if you're trying to be a little more formal, there are a lot of other reactions to consider. Just as one point, you can have Bremsstrahlung from one of the ions. This cross ions are pretty heavy. So this is relatively small cross section, but it's not zero. So 1 over k photon energy spectrum. So it's logarithmically divergent. And that, there's an issue. There's also pair production. You can produce a row and then also have a 2-photon interaction that produces an E plus E minus pair. The cross sections for this are colossal. It's about 200,000 barns for lead-lead collisions at the LHC. If you have a UPC collision that's not too far away, the probability of getting a pair is more than 1. Another way of saying that is the average number of pairs for B equals 2RA is about 2.5, presumably with a Poisson distribution. Most of these pairs are pretty invisible. The lepton PT is peaked at a few times the electron mass, and they tend to be at large rapidity. So we don't see them, but we could design an experiment that would, and we would, they matter. And in short, so there are many ways to have additional unseen particles in these reactions. These are very small kinematic changes, but they break the exclusivity of the reactions. And good Walker requires exclusive reactions. And one person who I won't give a name here, because I'm not sure how she would feel about being quoted, made a comment at one point. So how coherent is coherent enough? And I think that is actually a fairly good way to think about it. Okay, So there's another issue with good Walker that comes up. If you think about lead or gold nuclei, they're pretty similar. You know, everybody in here thinks in terms of partons mostly. You know, they're Wood-Saxon distributions, and they have about the same radius, and you'd expect them to have very similar shadowing, right? However, if you look at them at a nuclear shell model, they're very different. Oops, that should be KEV. So, you know, and this comes about, you know, when you ask about how can you have a nuclear excitation. Excitation is endothermic, means you have to transfer energy to the nucleus. Typically, to emit nucleons, protons or neutrons, this requires, you know, 5 to 7 MeV, depending on the details. If one hypothesizes that this proceeds by single particle excitation, which I think there's data, you know, this curve here is consistent with emission, you know, the slope you expect from coupling to a single nucleon. Doesn't tell us what's happening at very small t, but at large t, we have pretty good evidence for that. Then, you know, you can take this energy transfer to the nucleon and ask what momentum does it need, and it's somewhere in the order of 100 MeV over c. So that tells you if you're looking at incoherent interactions with a PT less than of order 100 MeV over c, it's not proceeding via nucleon emission. It must be happening some other channel. And the only other channel that exists is photon emission. So for lead, the lowest excitation energy in the shell model is 2.6 MeV. And that, you know, and that corresponds to, again, in the single particle excitation hypothesis, of a PT of around 70 MeV over c. However, for gold, it's radically different. I apologize, that should be KEV, which is, those of you familiar with the shell model, this is a very low energy for an excitation, but that's the way gold is. Lead is doubly magic, gold is not. And so then that corresponds to a single nucleon recoil of about 12 MeV.
Yeah, but states with that low excitation energy are not single particle excitations, they're collective excitations.
Okay. If you want to say that more than a single nucleon is hit, then these momentum transfers become smaller.
Right.
So, you know, you can, I think, still take these as, you know, minimum. If you change that 6 to 12 and the 70 to 35, that would strengthen my argument.
Yeah.
So, the point is, in this region, between about 100 MeV over C and 70 or 12, you're having single nucleon excitations, and in particular, between 70 MeV, or whatever it is, and 12 MeV, you can have excitation in lead, but not in gold. And so this kind of means you can have incoherent excitation in lead, but not gold. And that sort of breaks the point that I started with, which is that lead and gold look very similar at high energies. You know, the shell model comes in here, and does not seem to be any way around it. There are some ways one could test it. You would need some detector to look for these very soft photons. I think such an experiment is possible at Jefferson Lab, but it's not easy. So another way to look at this is to, you know, ignore good Walker and just take a picture where you sum the reactions where the targets are indistinguishable. And then you do that, you get a pretty standard thing. You sum over the amplitudes where AI is the amplitude for interaction on a single nucleon. And then, you know, there's an EVIK dot B, which should be BI, you know, positions of the nucleon. So this means that if you have a transverse momentum that's where kV is less than h bar, then this exponential is 1, and you're adding the amplitudes and then squaring. And this is the coherent emission, you know, d sigma dt and t equals 0 goes as n squared. On the other hand, if you're looking at high PT, you get the exponential has kind of a random phase, and the cross-section goes as n, and you can kind of see that explained here. Here you have this n squared, and then here n. And so this explains a lot of what you see. It gives you a nice, actually, transition between the coherent and incoherent regimes as k arises. You could make this more sophisticated. You could add multiple interactions a la Glauber to include shadowing. You could include these nuclear excitations regime by summing over partons rather than nucleons. And this in some ways is very nice. It can accommodate the gradual loss of coherence. On the other hand, it doesn't really say anything about what happens to the target after breakup. And furthermore, this gives you pretty much the same answer as good Walker for coherent interactions. On the other hand, it pretty completely breaks the relationship you expect for incoherent interactions. And this is an important point because we're starting to see papers that relate incoherent interactions to nuclear fluctuations. So there's a bunch of ways to test this. You can look at coherent photoproduction with nuclear excitation or in peripheral heavy ion collisions. I think we've already seen those, and that we see both of those reactions. It'd be nice to have somewhat more quantitative data, but it's coming. The other things you could do to explain it, one is look at coherent photoproduction where you have region exchange. These are reactions involving the exchange of quantum numbers. And this would be things like photon, let's say, going to an A2 plus 1320, which carries charge, plus the nucleus that's one less charge, A minus 1, changes the proton into a neutron. And the question would be, can you see coherence over all of the protons in a target? And I think most theorists, the answer would be a hard no. I tried to present this once about 10 years ago and was not well received, but I'm no longer convinced of that. If you can see reactions where you have nuclear breakup, why couldn't you have coherence over?
Yeah, the question of coherence has to do with when you're changing protons into neutrons, and the protons are in different single particle states if you just take the shell model. And so the A minus 1 on the right is different for these different levels. And so you're going to a different final state, so you really can't add the amplitudes. That's what theorists say what they are.
Yes, right. I still think this is interesting enough to be worth pursuing. And would I will talk about how this might be possible with LAs.
Does the A2 have a negative charge state?
Yes.
So then you're changing a neutron to a proton, and
right.
Heavy nucleus has a neutron excess, and there you might have many neutrons in the same shell. In that case, it would work.
Yes, you are foreshadowing my next slide.
Oh, okay.
So the other thing that would be interesting would be to actually look at the sigma dt for incoherent production in lead and gold at low T. This doesn't seem to be possible with UPCs because you're too likely to have these additional photon exchanges here. But it could be doable in a fixed target experiment, particularly at Jefferson Lab, where you could look at rho photoproduction on nuclear targets, lead and gold, put a germanium detector near the target for one of the existing spectrometers, and this measurement seems doable. Backgrounds would be an issue, but this would let you actually measure, photon emission as a function of PT, and you can see if things drop out and really see what's going on here. So for these A2 1320 production, some years back, Yao Pengzi and I did a study we just looked at proton targets here, looked at, basically looked at fixed target data on A2 1320 plus photo production, parameterized it, and then plugged that into with the photon spectrum from a heavy nucleus in AP collisions. And we saw this look moderately doable with one big caveat. The cross sections are quite reasonable, 170 microbarns at RIC and 560 microbarns at the LHC. It's large enough. It decays with a 70% branching ratio to 3 pions. That's pretty easy. The problem is shown by this plot here. Production tends to be at forward rapidity, especially at the LHC. This is out of the range of the central detectors. It might be within range of the star forward detector, or might also be within the range of LHCb, or when it comes maybe in the LH focal. So there are some possibilities here, but it's not going to be particularly easy. That said, I would very much like to see LHCb work for this. So if you want to look at on ion targets, as Jerry said, you can look for production of the A2 1320 plus and the A2 1320 minus, and it would be very interesting to see if you have coherent production in either or both. The interesting thing is if this works, you can compare production of both. You have a model that will give you the proton and neutron radii of heavy nuclei in a single experiment with very small systematics. Or maybe, as Jerry said, you will get partial coherence, but it would still be really interesting to look. You can also use these reactions then to study exotica. And one example we consider was the Z sub C plus 4430, which is one of the XYZ states. It's a tetraquark or a meson molecule or something like that. And these are produced at somewhat smaller average rapidity than the lighter states. And if you have the coherence, this could become part of the UPC program. Yeah. So now I would like to change gears a fair bit and talk about vector meson production and interference. As I said,
Sorry, so before you maybe
Okay.
switch that, so for the Z measurement, sorry, that's the left. The rapidity I wanted to ask was the rapidity distribution.
Yeah.
Okay, so that's still
it's
some
not-
LHCb thing.
Yeah, I mean, it's not bad for RIC, but the energy is kind of low for RIC. And LHC, it's sort of out of range.
Okay, thanks.
Sure. I mean, you might actually be able to do this with a focal, depending on how it decays. So, here, we get into this issue of, interference and wave function collapse. And I'm not going to read this cartoon, but it really does nicely encapsulate a lot of the confusion. So, first, before I talk about new things with multiple vector mesons, I thought it would be worth summarizing what we've seen with single mesons. And here we see interference basically from these two diagrams here. Either nucleus 1 emits a photon, which scatters off nucleus 2, or vice versa, nucleus 2 emits a photon, which scatters off nucleus 1. These two reactions are indistinguishable. And so, therefore, you add the amplitudes, and in fact, going from one diagram to the other is like a parity transformation. Vector mesons are negative parity, so you actually subtract the amplitudes, so it's A1 minus A2, but then you also have to move the vector meson from one production point to the other, so there's this propagator e to the I k dot b, and then you add those two amplitudes and square, and these are depend on the photon energy, but if you sit at y equals 0, the photon energies for these two solutions and a given rapidity are the same. So take y equals 0, then you can see the peak because of this e to the I k dot b. The cross section will drop as pt goes to 0. One interesting sidelight is if you were to do this experiment at the Fermilab Tevatron, which of course is long gone, but you could do it, then going from one diagram to the other is like a CP change. So you get a sign that's A1 plus A2 with E dot B. To make a long story short, this is data from STAR, and you can see there's this turnover at small pt, which is very close to what the theory predicts. STAR measured about 84% of consistency with the theory, and this is done for two triggers. One is this minimum bias trigger, and the other is this topology trigger. The topology trigger did not require nuclear breakup. The minimum bias trigger did require nuclear breakup, and you can see there's interference in both. It is in fact more prominent in the minimum bias trigger. That's because the median impact parameter here is smaller. Because if you require multiple photon exchange, you're biasing yourself towards smaller impact parameters. You can also go further and say, well, these photons are polarized. Excuse me, I skipped one slide. Let me go back for a second. So these photons here are near real. That means they're linearly polarized, transverse to the direction of the momentum. In other words, if you sit here at a point, the polarization parallels the electric field vector pointing outward from the emitting nucleus. S-channel helicity conservation tells us that the vector mesons have the same polarization as the photons. In other words, the pomerons do not affect spin. This has been known for decades, at least since the 1970s, studied by many fixed target experiments, plus by Hera, Starr, and Alice. And these, basically, you can parameterize the polarization in terms of these angular coefficients, and basically they're consistent with S-channel helicity conservation. One interesting aspect of this is that if you have these two nuclei, like here, tells you the two photons are basically polarized in opposite directions. And so the polarization is important because vector mesons, they tend to decay, let's consider rho to pi pi. The pi plus and the pi minus tend to follow the photon direction. This is sort of what you expect. You can think of it as the vector meson being a dipole, and dipole is aligned along the electric field vector, and breaks up that way. And this is important because that introduces a relationship between the PT of the vector meson and the PT of the pion decays. A photon comes in, you produce a row, and you get basically back azimuthally back-to-back pions. And Starr has taken advantage of this. They did these very nice series of fits where they include this azimuthal modulation, and they were able to make very, very precise measurements of the nuclear radius of gold.
Sorry, before you go forward, I just want to still understand the basic idea of this wood water.
Yeah.
And then, so for example, this figure, the wood substance. So how you get this plot is from the substance you have you can get the profile in the as a function of the interferometer, and then so you can have a profile in the transverse plane, right? And then you just Fourier transform that from the B to the T, but it's PT.
No, this is actually simpler than that. This is a model comparison. So the data is the data.
Yeah.
And then what they do is, they have a model that encompasses, a more sophisticated treatment here, where you include the sizes and shapes of the nuclei. and you add the amplitudes for all of the individual nucleons, and that, and then you integrate over, all of the possible impact parameters, and they do that for different models. So I think the Wood-Saxton model.
So you have nucleons. It's like
inside.
It's not like just you have the fluctuation of the each nucleons, or is it just the number of the?
I don't think STAR had the fluctuations. I know the calculations I did not. They're
because I just imagine if you have this fluctuation of nucleons inside, and then you have the profile, this fluctuating profile in the transverse plane, it would change the results, right?
Well, I think the fluctuations will average out because, in good Walker, you're studying for coherent production, it's the average nuclear configuration. And if you do it even in a semi-classical thing, the fluctuations will still average.
You see the incoherent.
But this is coherent.
Okay. Thank you.
Yeah. And the difference here, the Wood-Saxton is they just did the nucleon. I think Model 2 incorporates this angular modulation, and you can see it does a much better job of fitting the data.
Can you do the same thing in incoherent cross-section and then try to see the fluctuations?
Well, then the question would be, how would you select the incoherent events?
Okay.
One problematic aspect of this plot here is that, is that in this region here at low T, you're dominated by coherent interactions, and there's enough enough nucleon emission from additional photon exchange that you really can't measure the incoherent production. And then at larger T, this is a little misleading in that, it looks like incoherent dominates over this range of T, but, this peak is more than an order of magnitude higher.
So I think I got confused with the terminology. So this red one is from the fluctuation of which one? Like one is from incoherent.
The red is from incoherent.
Which is sensitive to the fluctuations of the
if you believe good Walker, yes.
Okay.
I'm on the fence about that.
Okay.
But it's incoherent, it's a smaller target, it's a single nucleon. So, it's pretty flat. And, one of the reasons one might question whether it's sensitive to fluctuations is this is a good fit to a single nucleon. And there's actually newer data I could show you later that makes that crystal clear. But if you're talking about fluctuations, it's not obvious why the slope here, or even the shape, would be consistent of that of a single nucleon.
Okay, I just thought that it would be interesting to extract the fluctuations.
Well, yeah, I mean, there are people who've tried to do that, but there's an assumption there about, it being due to fluctuations, and there's also assumptions, about you're only seeing part of the cross section because you can't measure the incoherent cross section at a small t.
Thank you.
Anything else? So, anyway, the main point here is, we see this interference, and it's pretty clear it's there. It's also worth pointing out, this is an example of the Einstein-Podolsky-Rosen paradox. And the way you can see that is from this diagram here. You can think of these ions as near point sources in rho, and that's because the nuclear radius, and you could add in an extra one Fermi if you wanted, to account for the Pomeron range, is less than the impact parameter. To take the example from Ali's, nuclear radius is 6.5, 7 Fermis, and the typical separation is, I think, 100 Fermis at Alice if you do not require neutrons. So these actually do act kind of like two fairly near point sources. The rho decay almost immediately, gamma, beta, c tau is order of less than 1 Fermi. So they're actually nearly point sources of pi plus, pi minus. And so at the point at which the rho wave functions have decayed, they have not overlapped. So there's no way the interference can involve the rho directly. It must develop later. And later, when the wave functions, called expanding wave functions from the two nuclei overlap, you have pi plus and pi minus. So that's where the interference must come from, the pi plus and pi minus overlapping. But by the time they overlap, the pi plus and the pi minus are well separated. So how do you have this interference that involves well separated pi plus and pi minus from here and well separated pi plus pi minus from there? The only way is with a non-local wave function. And so you have a non-local wave function. This is an example of the EPR paradox. And one interesting point you learn from this is that wave function collapse has to occur after the rho zero decays. So it tells you that particle decay does not collapse the wave function. Yeah.
So is the interference happening between the pi plus from one row and the pi minus from the other row?
Well, see, the interference involves you have interference between the pi plus and the pi minus. If you just looked at the pi plus, you wouldn't see anything. The way the interference manifests itself is, this dip at PT of 0. So you can, it's the PT of the pi plus the pi minus.
I guess just from this diagram, it looks like there are two rows being produced. Is that the case?
Well, there's amplitude. There are row amplitude coming from two different sources.
Oh.
You think of these in terms of amplitudes.
Oh, okay. But what's actually measured is one row 0 from one event.
Yes.
But we should think of it as there being contributions from both channels.
From both amplitudes from both possibilities.
That makes sense.
Yeah, and to get the interference, you have to have the interference. The pi plus and the pi minus are involved, have to be involved because it's the sum of their PT that is the signature, and they're well separated. So now, with that, we'll move on to talk about multiple vector meson production. It's a case where you have basically, two ions interact. Each one emits two photons are exchanged and could have involved either ion. Could have both of them could come from one ion or from the other ion or one from each. And you can calculate cross sections pretty easily using this factorization. That means you describe the cross sections in terms of probabilities at a given impact parameter. And then just the cross section is you just integrate over transverse impact parameter space and multiply the probabilities. This is exactly what we did, here with, where we looked at rho photoproduction plus mutual gluon excitation, probability of producing a rho, probability of exciting one nucleus, probability of exciting the other nucleus, and it works quite well. So, and then calculate cross sections, that was extended. Mariola, Kluzik, Goenda, et al. Calculated cross sections in kinematics. Actually looked at rapidity distributions if you have multiple rows and pair masses, etc. And seemed pretty reasonable. One point to make is that one can ask, why hasn't this been seen? The cross section for rho 0 is about 20% of the cross section to have a single vector meson producing a 4-pion state. So that's a pretty significant background. I think there are ways around it, particularly with a large acceptance detector, like Alice 3, for example, to pick one. But that has not been shown yet, and we have not observed it. But it's still interesting to think about. Because it's probably close. It's likely that Atlas might be able to do this, or somebody working on it for a while. And so I'm going to talk about two aspects of multiple vector meson production. One is the angular distribution, and the other you can think of as the rapidity and PT distribution. And here, by angular distribution, I mean the angular, if you imagine the two nuclei collide, talking about the azimuthal angular distribution. You know, what direction does either, you know, do the pions go if you have a row, or if you have a Coulomb excitation, you know, what direction does the neutron go? And this is basically, this angular distribution is governed by Klebsch-Gordon coefficients. It's pretty straightforward. You have, you know, two ions collide, and one of them is excited in, say, a giant dipole resonance in the case by emitting a neutron. You know, that neutron will come out from the interaction region with some PT at some given angle, and you can describe an angle theta that describes its deviation from the impact parameter transversely. Similarly, if you have a row or producing a pi plus pi minus, or you could do this for J psi to EE or anything, you know, you have measure the pion distribution, you make an angle theta with respect to the impact parameter distribution. So if you just have a single interaction, this doesn't tell you much because you don't know what B is. However, except for this angular correlations here, you know, between, you know, the direction of B gives you a modulation in the pair PT, and then you have also have the pion PT, you know, the azimuthal distribution. But that's, you know, one indirect. However, if you have two excitations, then you can measure the angular difference between them. If you have two giant dipole resonances, you measure the angle, you know, azimuthal emission angle of one and 1 0-degree calorimeter, and then of the other 0-degree calorimeter. Or if you have a pi plus pi minus, you can get the angle that way. So what do you expect for these angular differences? So if you do it classically, it's pretty straightforward. You know, let's consider two neutrons from mutual GDR excitation. Both have this angular distribution given by cosine squared theta with respect to B. So you have B, you have one that makes a cosine squared theta distribution. The other also makes a cosine squared theta distribution. You convolute them and you get distribution 1 plus cosine 2 delta phi over 2.
What is delta phi? What is
delta phi? Is the angle between these two neutrons. Phi 1. It's phi 1 minus phi 2.
Okay.
However, if you look at it in terms of quantum mechanics, B is, you know, is unobserved, so it's undefined, so it's essentially random. There is no preferred direction. So when you first see your first neutron, that orientation will define the direction of the photon polarization for the next neutron. Essentially, you're collapsing the impact parameter to be along that direction. And this is probably going to sound really odd, but think of it, you know, like if you're doing, you know, you're looking, you know, imagine you have a source of photons with the same polarization going in two directions, just like, testing Bell's inequality. You know, you have two polarizers that you can choose the random direction. You know, photon goes through one, that determines the direction of the polarization, which you measure the other. It's the same as with these neutrons. So you have one, you see your first neutron, that determines the direction of the polarization for both of them, and therefore you get just essentially a single cosine squared theta delta phi here, different from the classical one. And this plot here just shows the difference, you know, and you can see the quantum one goes to 0 at pi over 2. You know, this is basically just a statement. If you do a Bell's inequality test and you have two polarizers that are separated by 90 degrees, nothing will get through both of them. And so say, if you have the neutrons, they will never be pi out of 2 out of phase. No complaints about that? Okay. Yeah, so this is just like, Bell's inequality test. You have a laser, you produce 2 photons that are polarized in the same direction, and you select things. The only difference here is the polarization is self-analyzing rather than requiring polarizers. So this actually gets even more interesting if you consider cases where you have more than 2 of these vector particles. And we can actually study this in UPCs. We've seen n=3 reactions in both star and Alice, where you excite the 2 nuclei, and if you select single neutrons, those are giant dipole resonance excitations and a rho 0. And so what we have is the first neutron, or pi, sets the polarization direction. And here's the first one that's observed. We can come back to that in a bit. Then you see the second one, and it has a cosine squared theta distribution with respect to the first. But then that also, in addition, resets the direction. And an analog here that I think makes sense, if you have a photon going through a bunch of polarizers, it gets through the first polarizer, so it's vertical, and then you try and send it through a horizontal polarizer, it won't get through, they're 90 degrees apart. However, if you put a polarizer in between the 2 at a 45-degree angle, then some of the photons will get through because they're come in, go through the first polarizer, they're vertically polarized, they make it through this cosine squared theta probability of making it through the second. And if the ones that emerge are polarized at 45 degrees, and then, so some of those can then make it through the horizontal polarizer. So you have your first decay, and then the second one, and then the second one kind of resets the polarization direction. And then the third neutron, or pi, will be distributed according to the angle from the second decay. So it will be, p delta theta 2,3 is cosine squared theta 2,3 with respect to the second ion or neutron. The interesting thing here then is that, seen in this light, the order of the observation matters. And so then you have to ask the question of what constitutes observation. And this is something we now actually would have some experimental access to. You might say it's interaction with an active detector element. So, we get back to this example here. Well, the rho 0 is going to produce pions, which are observed in the silicon vertex detectors of any collider experiment after traveling a few meters, whereas the neutrons have to travel about 100 meters to get to hit the ZDCs. So clearly the rho would be this first decay, but one could imagine as a Gedanken experiment, but maybe as something that is also possible, you could move the ZDCs in or out a little bit and control which is the second and which is the third. And you could actually observe this because, the distribution, the angular difference between the first and second decay will be smaller than between the first and third decay.
But doesn't the polarization get set before observation? Because the polarization is set by the decay of the neutron, right? But that happens before you observe the.
Well, I would argue that the polarization is set when the wave function collapses. And argued I showed before that wave function collapse happens after the decay, and so we don't know may not know how far after, but if it's not the decay, the obvious time for it to collapse would be when it interacts with the detector, and that's or one could also have it collapse even later. The question about what is observation? Is it changing the detector, or is it being recorded on magnetic tape, or is it when the physicist looks at it, or the whole sort of philosophical thing.
5 months after the data is collected. spooky action.
Right. But the point is, this gives you a handle to actually look at this experimentally.
Good, Spencer.
Yeah, okay. So I'll go through the other part, which is that's looking at double vector meson production. And short answer is, if you're looking for at non-identical mesons, you get these 4 diagrams that contribute, and I'm sorry, this should have been on me row, and it's because you have 2 photon directions and 2 time ordering. Sorry, here we are. So you get these 4 diagrams, and turns out, however, after lots of algebra, it turns out not to be that interesting because it factorizes into the product of 2 single meson emission spectra. So this is just like taking 2 interference as I talked about before, and gluing them together. Production disappears when either meson has PT of 0 and line equals 0. It just looks like the product of the 2 cross sections. However, if you look at identical mesons, things get more interesting. You get 8 diagrams. This is because you have twice as many diagrams, since you can swap the 2 final state mesons. Basically, there's 2 ways for photons with momenta Q1 and Q2 to produce these photon momenta to produce mesons with momentum P1 and P2. Another way to think about this is if you have the photon fluctuates to a virtual vector meson, which then scatters off of the nucleus and emerges as a real vector meson. One can have scattering, 2 sets of scattering that will map, those 2 photons into the 2 mesons in different ways. This gets complicated, so I'm just going to talk about a couple of interesting cases. One is where you have identical mesons, you're producing them at forward rapidity. That means you kind of know, at least on a statistical basis, which nucleus emitted the photon and which was the target, and it's the same for both. You could then write this probability shown here, and what you see is you get coherent enhancement when K1 plus K2 dot B is less than H bar. There's also longitudinal coherence. I'm not going to go through that here. Involving the longitudinal momentum transfers being small, and this can be translated to a rapidity difference. And this, because you have K1 plus K2 here, it's a tighter coherence condition in the single mesons. But when that is done, the cross section is twice that for the non-identical meson case. And this is essentially called superradiance. And there actually are similarities with HPT and other things here. I'll go quickly. It gets more interesting, and this is probably a Gedanken experiment, but not necessarily. If you consider more than 2 forward mesons, you have M mesons, there are M factorial diagram, and the probability scales like this, M factorial times the probability to the M. And this is interesting because if you go to large M factorial increases faster than the probability to the M power gets smaller. The probability for producing a row at the LHC for B equals to RA is about 3%. So you can think of this potentially could be a vector meson laser. There are a bunch of, you look at it, a lot of similarities. The phase space drops as 1 over M because you're summing over all of the nucleons, all of the photons here. There is a limitation because you can only get a fraction of the energy from the photon field. It's not clear what. This probability is pretty small. It's, not completely clear how far you can follow this. Certainly you can study n equals 2 and n equals 3 and maybe a bit further. This also opens an interesting possibility of, can you see stimulated decays? If you produce enough rho, I'm almost at the end. In the same state, then you should, if you have a bunch of rho in a single state, one of them decays, you should have the probability of getting stimulated decays into the same final state. Similar criteria is for short-lived particles. The coherence time has to be larger than the particle lifetime. Their momentum have to be close enough together. And you can see this by looking at, for event-by-event fluctuations, for example, and how J psi decay, or you can see it in terms of this angular correlations, which would be, look at correlations between the 2 pi plus and the 2 pi minus. So my conclusions, coherence is an interesting and subtle topic with important consequences. The Good-Walker paradigm relates coherent and incoherent photoproduction to the average nuclear configuration and configuration fluctuations, respectively. In Good-Walker, coherence means that the target remains in the ground state. That disagrees with some experimental observations of coherent photoproduction. An alternative approach to coherence, adding amplitudes, so like this equation here, can explain the data. Adding amplitudes allows some new coherent UPC channels, including coherent photoproduction of charged mesons, and UPC production of multiple vector mesons exhibits many interesting aspects of interference, azimuthal angular correlations, a la entangled photon pairs, and superradiance for identical vector meson production in the forward direction. Thank you.
Thank you very much, Spencer. This was really interesting. Let's see if we have any remaining questions. Let's see. Doesn't seem to be the case.
Jerry has one.
Jerry is still clapping.
Yeah, I don't know how to stop it.
Jerry, is that a clapping question or you actually have a question?
I actually still have a question, but I don't know how to
Please
make
go
it
ahead.
go away.
That's all right.
On this business of incoherent when you excite the nucleus seems kind of strange to me. And if I look at some of your data, it shows a decrease in cross section when PT goes to 0.
Right.
Which,
Here, yeah.
and that's symptomatic of inelastic scattering.
You mean this data here?
Yeah, that goes down, and there was another slide too, either
Right.
before or after. You're going down. If I look at the lower plot, there's not a forward peak. There's a forward.
Right.
That's typical of exciting the nucleus because you have orthogonal final state. The initial and final states are orthogonal. So the cross section should vanish when the momentum transfer is 0, and that's what you see. And in that case, not all of the nucleons contribute, and so that's why I asked a question about the A dependence. In the A dependence that you would have for coherent, you had as n squared, which is fine. If I look at this peak, the peak here, near where your arrow is, you have a forward peak at non-zero PT. Does that go like n squared? Or it's only gold nucleus, so you can't tell from that plot. But if you did another nucleus, would it go like n squared or something less? I think it should be less.
I would argue that this peak, first of all, it's consistent with detailed calculations of this interference that I went through. And one thing you can look at, this way to see that, this interference is strongest when A1 equals A2, i.e. at mid-rapidity. And so if you compare the plots on the left, and I'm sorry if I had realized there would be so many questions, I would have made these larger, but the plots here on the left are for small rapidity and then larger rapidity. And you can see that the interference is reduced, especially here. The interference is reduced when you go to large rapidity, which is what you would expect from this bidirectional interference, and I think not what you would expect from the forward scattering that you just described.
Okay, good.
All right. Anything else?
Yeah, probably a very naive question. Like in the last part, we talked about the 2-particle and 3-particle production. Are they exclusive? Do you have any other particle produced, or you just select 2 or 3 out of all the particles?
Well, I mean, I was naively assuming, you know, just 2, but there's not, you know, there's nothing in there that would require it. If you do this, this formalism here, the calculation, you have the d squared b and then p1 and p2, and then one could add, some p3 here, or really, to be complete, you could add it in terms of p3 plus not p3. And I'm really considering both of those, taking it as one.
Yes, thank you.
All right. Spencer, thank you very much again.
Sure.